And so but why we are using CMOS or MOS technology mainly? Okay, so in old days, okay, you might have read that in the Nobel Prize for the transistors, okay, it was given to Shockley, Bardeen and Brattain in 1956. Okay, it was for something known as a bipolar transistors. Okay, so Shockley was the main person inside behind this bipolar junction technology. So for many years, bipolar junction transistors rule the semiconductor space. Uh, but the MOSFET, they have some intrinsic advantages over MOSFET, okay, over bipolar junction transistor. First thing is that a bipolar junction transistors, you may typically draw a transistor in your textbook is something like PNP, but the actual device, okay, so the real device doesn't look like this one. Okay, so in early 50s, people used to make something like this one. Okay, they take a N type layer and they put two P type layer on either side. Okay, then it was true. Okay, so they were called as alloy junction transistors. But later, when but they had some issues. Okay, they are not good for manufacturing. Okay, so then people moved into something known as diffuse device. Diffuse transistors. Okay, so the bipolar junction transistors, they were made using a technology known as double diffusion. So if you take a substrate here, this is P, suppose this, and what you do is that, okay, you do one diffusion, that is this N diffusion, and you do another diffusion here. Okay, this P. So this is how they made the bipolar junction transistors even today. So you have this double diffusion. So your emitter is on top, the base is here, your collector is here. In the bipolar junction transistor, the most critical device dimension is nothing, is the base width, the width of the base. You might have studied you want the base width should be as small as possible. Okay, typically it should be smaller than the diffusion length of the electrons and holes. But this base width is in the vertical dimension. Coming to MOS transistors, the most critical dimension is the gate length. Okay, this gate length, again this device, this is a gate length. Okay. So, but this gate length is in the lateral dimension. Suppose if you are a process engineer and somebody asked you, if a circuit designer came and asked you, okay, suppose he is a bipolar, if a circuit designer of a bipolar junction transistor, he asked like, okay, whether do you have, is it possible to, I want, what I want is a set of different bipolar junction transistors and they have different base widths. Okay, so the base width of, suppose I want a 10 different base width. So is it possible to make 10 different base width in a single wafer? Okay, it's a single chip. So it is very difficult to make because you are doing diffusion. Okay, so it is very difficult to make on a same chip 10 different bipolar junction transistors with a 10 different base width. It's very complex and it's a very expensive process if you want to try that, because if you do one diffusion, okay, you may be able to do the first diffusion. If you want to mask that, okay, if you want to do, and if you want to do another diffusion in the other area, what happens is that because the diffusion is a thermally assisted phenomena, the second diffusion may affect your first transistor. And other things similarly, then you need to worry about all the thermal budgets very early and you have to design the first transistor by taking into account all the other what is the thermal budget of all the other 10 transistors. So it is very difficult to make bipolar junction transistor with a different base width on a same wafer. But coming to MOSFET, okay, because it's in the gate length is in the lateral dimension, it is very easy to make MOSFETs with a different gate length on the same chip. So that is what circuit designers like. Okay, so if they want depending upon your current requirement, okay, they may require short channel transistors or long channel transistors, or depending upon whether it's a digital or analog application. Because the gate length of the transistor, okay, it is defined by something known as a lithography. Okay, so you use on a single step itself, you can print gates with the different widths, different lengths, or whatever called different size. So that is possible with only for MOSFETs. So that is why. So the critical dimensions you can print. Okay, so that is why on a single chip or a single wafer you can build a MOS transistor with a different gate length, which is not possible or which is very complex in the case of a bipolar junction technology. Other thing is that the bipolar junction technology, okay, there is in NMOS, if you connect an NMOS or a, sorry, in a MOS technology, if you connect an NMOS and a PMOS, so you can create something known as a CMOS. So the CMOS has very low standby power dissipation. So in the very early days, the CMOS was mainly used for low power applications like watches, cameras, calculators, and all. But the bipolar logic technology, okay, it always leaks. Okay, there's always so what it does is that it limits the number of transistors in the chip, because if you remember last class, even if you are leaking like 10 nanoamps or 100 nanoamps, okay, by the time if you put 100 million transistors, okay, you are leaking something around 10 amperes. Okay, so that's not possible. Okay, so it limits. So if you are trying to make a chip using only bipolar junction transistors, here dissipation, okay, the power dissipation limits the number of transistors for a bipolar junction technology. And other thing is that, okay, if you look at the MOS technology, okay, the MOS is a very symmetric device. Okay, so as I said in the last lecture, okay, so this source or the drain, okay, they are similar. Okay, it only the potential determines which is source and which is drain. So if you apply drain here, the current is in this direction. If you apply reverse the voltage, the current is in the opposite direction. And the doping profiles, okay, the source and the drain, they are being doped at the same level stage. So the doping profiles, whether you cut in this direction here and here, the doping profiles, if you try to plot, they are the same. But this is a bipolar junction device. Okay, so this bipolar junction transistor. Okay, so see, this is emitter. Okay, so the emitter, this is a base here. So this is a double diffusion. So emitter is here, base is here, this is a collector here. So you can see if you take a cut here in this direction, okay, the doping profile is going to vary a lot. And for the performance of the bipolar junction transistors, emitter is doped heavily. Okay, then base, then collector. So you cannot interchange the emitter and the collector terminals of for a bipolar junction technology, and you cannot expect the same performance. But that is possible in the case of an MOS transistor. Okay, so these are the three critical reasons, okay, that made the MOS transistors, okay, dominant technology. Okay, so roughly around, if you almost around 80% of all the transistors, okay, not more, even beyond that, okay, it is being all made by MOS transistors. So when we discuss about subthreshold, threshold voltage, okay, one of the simple models which we used was, okay, if your gate voltage, okay, if your gate voltage is less than Vt, okay, we said that, okay, it could be the current could be assumed to be 0. So this is fine. Okay, so even your first order model, okay, it says that current is 0. Okay, that is why you can see this is a Vg minus Vt. Okay, somebody asked about this question. Okay, why there is a Vg minus T term in the current. Okay, so this whatever the current expressions, it is valid only for Vg greater than Vt. So if you are approaching MOSFETs with that model in mind, okay, that model says that there is no current flowing through the channel when the gate voltage is less than Vt. But that is not correct. That is because we saw that what the gate does is that it modulates the barrier between the source and the channel. Okay, so if you look at maybe if I go back here, if you look at that band diagram, right? Look at this band diagram. So what the gate voltage does is that, okay, it modulates this barrier. Okay, there is this barrier here, the gate voltage. Suppose in the case of an NMOS device, the gate application of a positive voltage at the gate, okay, it reduces this barrier. So if you are continuously varying the gate voltage, we are increasing the gate voltage like this, the barrier keeps on reducing continuously. Okay, it's not like the barrier is something like this one. Okay, the barrier also keeps on reducing continuously. So and also the electron, right? If you have studied in semiconductor physics, the electron, as you go higher in energies, okay, as you go higher in energies, the electron distribution is something like this one. Okay, there is a peak, okay, somewhere around kT by 2. Then it decreases. Okay, so as you go higher and higher energies, the electron distribution reduces. So what it does is that, okay, if you lower the so earlier only these electrons, okay, only these electrons were able to cross this barrier. Now if you reduce the barrier, what happens is that more electrons will be able to jump over this barrier. Okay, and so this is a monotonic function. Okay, So what is it? What it does to the current is that, okay, current also will slowly increase. Okay, so that means that even below threshold voltage, there is some current flowing through the transistor. So this comes from the physics of this device only. So there is always injection, but the amount of magnitude of the injection is very small. So at gate voltages lower than threshold voltage also, there is some current flowing through the transistors, and we call that current as the subthreshold current. So for example, this is the same thing which I was saying. Okay, so this was a barrier here. When you increase a gate voltage, okay, you are reducing the barrier, and all this. So earlier only, suppose in first case, okay, only this electron was able to jump over the diffuse. When you reduce the barrier, all these electrons can flow over the barrier. So this is a continuous increase. Okay, so what it does is that since the number of electrons is exponentially varying energy, when you increase the gate voltage in a linear fashion, the current increases exponentially for some region. So then what happens is that the channel is on, then it will be taken over by something known as a drift transport. So this region, it is known as a subthreshold region. Okay, so in the subthreshold region, the current increases exponentially. So the MOSFET, the switching characteristics is not something like this one. Okay, so this is what you would like to have from an ideal switch, and so the MOSFET or any transistor is some kind of a realization of any switch. Okay, so but you cannot get something like an ideal switch here. So this device, so it goes up. Okay, so this rate. Okay, so there is a metric for this name. It is known as subthreshold swing. Okay, so it's a metric. Okay, the units are millivolt per decade. When you vary by, so what it suppose the units are typically, okay, for real devices, planar devices, the subthreshold swing of the transistors is somewhere around 80 to 100 millivolt per decade. What it means is that if you vary the gate voltage by plus 90 millivolt, your current increases by 10x, okay, 1 decade. That's what it means. So for this kind of a transistor, okay, this kind of a transistor, what is the subthreshold? So that is, so even if you vary the gate voltage by a small amount around this region, you go from on to off, right? So you require only very little gate voltage here. Okay, so that is why for this is for an ideal switch. Okay, the swing is something very close to 0, but that cannot be realized in a physical device. So the MOSFET, the planar transistor, the kind of transistor which we have been discussing, they are roughly in the range of 80 to 90 millivolt. But if you go for multiple gate devices, you can even lower it. Okay, somewhere around 65 millivolt per decade or something like that. And the theoretical minimum at room temperature, okay, it is somewhere around 60 millivolt per decade. So there is you cannot, that comes from this term. Okay, so I am not showing the derivation of this expression. So that comes from this term. Okay, so there is a prefactor here that is exactly 60. So that is why the minimum you can go is around 60 millivolt per decade. So this phenomena, the subthreshold current, right? Subthreshold current, it has been there for even a very long channel transistor, 10 micron transistor, but the currents were very low. So now the question is, we saw that there are various benefits of scaling. Now, but you have to be very careful when you try to scale the transistors. That because there are a lot of different second order effects which comes into play when you try to scale the transistors. So all these second order effects, okay, they comes under some name known as short channel effects. That is, those are the effects which come up when you try to make the transistor channeling smaller and smaller. Okay, now let us see what happens. Okay, what happens? Well, the first thing is that the threshold voltage of the transistors. Okay, we saw that the threshold voltage is only a function of mainly it is the doping of the device. Okay, doping and Tox, the Cox. Okay, so if you suppose let's do a simple thought experiment. Okay, so if you suppose I have given you a transistor and suppose I ask you to imagine like you are trying to shrink the transistor gate length. Then and when you for each gate length I am asking you to measure the threshold voltage. The threshold voltage, we saw that, okay, you are looking for the inversion. Okay, you are looking for inversion, and you are trying to measure that the gate voltage at which the channel is being inverted. So if I ask you to take those measurements and if I make a plot, then for an NMOS device it may look something like this one. Okay, for very long channel lengths. Okay, so this is like a 0.5 micron. Okay, for around 0.5 micron you are reducing to 0.4, something like that. Okay, threshold voltage doesn't change. Okay, that is what you have been. If you look at the expression of the threshold voltage, it is independent of channel length. But something interesting happens. Then what it does is that, okay, threshold voltage starts reducing. Okay, threshold voltage starts reducing with the channel length. Okay, so this was not there in that simple model. So other important thing is that the threshold voltage it becomes a function of VDS. Okay, depending upon what drain bias you apply, you get two different threshold voltage. Okay, that your threshold voltage becomes a function of VDS. So if you have a higher threshold voltage, if you have a higher VDS, your threshold voltage becomes lower. Okay, so that means the roll off is even faster for higher and higher VDS. So, so this is true for both NMOS. Okay, this is NMOS, and here this I have drawn for PMOS. Okay, PMOS, the absolute threshold voltage it reduces. Okay, absolute threshold voltage reduces like this one. So this this phenomena, the dependence of threshold voltage and on the channel length as well as on the drain bias. Okay, it was not very clear from the simple models. So now let us see what is it due to. Okay, for example, and here this curve. Okay, so this is the characteristic. Okay, so this is the characteristic of the MOSFET, because keep in mind this is the drain current in log scale and this is the gate voltage in linear scale. So these are characteristics. Looks like, okay, this is a subthreshold region. So typically, if you want to measure the threshold voltage in industry, what they do is that, okay, they specify some current. Okay, they specify some current. For example, it is a metric is like, suppose it's like 100 nanoamps per W over L. Okay, W over L. Then they measure the current. Okay, and they look at what gate voltages the current reaches this value. Okay, they call that gate voltage as a threshold voltage. Threshold voltage. So this is one way you can measure threshold voltage for very large number of devices. Okay, so this is how it is being practiced in industry. So they measure threshold voltage. So it's known as a constant current method. So there is a current. So depending upon the transistor W and L, they will be different. So this current will be different, and they measure the gate voltage at which the current. So then they plot all the threshold voltages in this plot, right? So basically, what you are seeing is that there is a roll off in the threshold voltage. So now the question is, okay, well, whether we can explain this roll off of the threshold voltage. That is one of the short channel effects, and there are other short channel effects also. There is something. Suppose you take the same transistor. You say you take the same transistor, and I am plotting the drain current, the characteristics. That is the drain current versus the gate voltage. Suppose yeah, I have kept the oxide thickness is 10 nanometers and the doping concentration is 3 into 10 to the power of 16 per centimeter cube. If your transistor gate lengths were very long, okay, if your transistor gate lengths were very long, then suppose this is the threshold voltage. This is the threshold voltage. Something like this one. So if this is a threshold voltage, so you can see for a very long channel transistors, okay, so there are two for every channel length. I have given two characteristics. Okay, well, that is for two different drain biases. One at 3 volt, other at 50 millivolt. So 50 millivolt, the transistor is in linear region, and at the 3 volt, the transistor, you are guaranteed that the transistor is in saturation. So if you measure the threshold voltage using some constant current method, suppose I assume the current is here. And the threshold voltage, okay, you get, okay, the threshold voltage is not very different between the linear mode and the saturation mode. Okay, that's what the same thing here. Depending upon, these are for two different drain biases. One is for the linear mode and other is for saturation mode. So for very long devices there is not much difference. Okay, it may be around 20 millivolt or 10 millivolt. Okay, you won't see that clearly in this plot. And there is another parameter known as off current of the transistor. That is, off current of the transistor is that current when your gate voltage is 0. If your gate voltage is 0, what is the current flowing through the transistor? Okay, so you may wonder why there is a current flowing through the transistor, because our drain voltage is not 0. Okay, if the drain voltage is 0, if all the biases are 0, then there is no current. But if your gate voltage is 0, substrate voltage is 0, but if it is some drain voltage is present, there is some current flowing through the device because of the subthreshold current. So if I scale this transistor, suppose I go from 2 micron to 0.35 micron. Okay, in the similar to that hypothetical experiment, I kept the TOX and the substrate concentration same. I only reduced the channel gate length. So then what happens is that, okay, this characteristics, okay, it moves up. Okay, that is what expected from the scaling. Okay, that you get higher current because as you scale the channel length, you get more and more current. But you can see, now you look at the dash characteristics. Okay, you can see in the subthreshold region you have this characteristics and this characteristics. There is a separation. Okay, so that means that the VT is going to be different. Okay, depending upon whether you are measuring in the linear mode or in saturation mode, you get two different VT, and the off current also is different. Okay, depending upon the drain bias you use here or here, you get two off currents. And if you compare these values, okay, if you compare these off current values for this device with the 2 micron device, you can see the off current is increasing, the VT is going down. And if you take the same transistor, if you scale further to 0.2 micron, 0.2 micron, you can see now the delta, the delta between the linear mode and the saturation mode is widening. Okay, that is what happens in the threshold voltage. You can see this delta is increasing as you scale deeper and deeper. And other thing is the off current is increasing. So in nutshell, what it says is that if you scale the transistor, just only the channel length, okay, you don't touch any other parameter and only scale the channel length, what happens is that your off current is going to increase and your VT is going to reduce. So this was not predicted by the simple models. Okay, in the simple model there was no off current at all, but in the VT depends on your channel length as well as your drain bias. That is what happened. So you need to do something. Okay, you cannot just do blind scaling. Okay, you cannot blindly scale the channel length or the gate length of the device and expect the same performance. So there is another effect. Okay, so you are looking at the subtract. So another effect is something known as punch through. Okay, so earlier in your, if you look at your idea, there's the ideal characteristics. Okay, what you had ideal characteristics, okay, your current was increasing, then it was coming constant. This was constant. So your current is saturation. But yeah, if you take a deeply scaled device, okay, if you take a deeply scaled device, okay, this transistor was not supposed to operate at this time. It was designed for a long channel device. If you only shrink the channel length and if you try to measure the characteristics, what happens is that, okay, there is no current saturation. The current is keeping on increasing. Okay, keeping on increasing. So and finally, what happens is that, okay, it increases rapidly and it undergoes a breakdown or something like that. So why is it increasing rapidly? Okay, that is because you saw that the depletion region is not, the thickness of the depletion region is not same at the source side and drain side. That is because in the drain side you have a large reverse bias and you have, this is 0 volts here. So what happens is that the depletion region, when you keep on increasing the depletion region, okay, the depletion region with this side, okay, this is a PN junction and this is a PN junction. Okay, what happens is that they will come and merge here. And rather than the current flowing through the surface of the device, okay, there could be large subsurface conduction. Okay, so this is known as punch through. Okay, so you don't want to operate your device here. So this is known as punch through, and typically you can eliminate it. Okay, you can eliminate it using something known as an anti-punch through implant. Okay, so depending early in the process, even before the gate is built, typically this anti-punch through implant is done. So they typically put your doping profile will be something large here. Okay, so this will prevent this punch through, because if you keep the doping concentration higher, that will reduce the extent of the depletion region to encroaching towards the source in the channel side. So these are some of the short channel effects. Okay, these are some of the short channel effects. Okay, so this you need to keep this in mind if you are interested in scaling the transistor size. Okay, maybe I will stop here. I will take up some questions, then I will continue. Okay, the first question is how leakage current can be controlled using threshold voltage. Okay, so the threshold voltage, if threshold voltage is, so this threshold voltage you can see, if your device has higher threshold voltage, your off current will be lower. Okay, so So, if for higher Vt, if the Vt is higher, off current will be lower. So, and similarly, if your Vt is lower, your off current will be large. So, in any design, off current will be large. So, in any circuit design, okay, typically you may have any logic design, typically you may have 3 or 4 transistors, okay, the same transistor with 3 or 4 different threshold voltages. So, that is because in a data path or something where there are some regions where you need a high speed device, in some regions you need a low leakage device. So, how they are built is that they are using implants, they vary the doping in these devices, so that there are some devices with higher threshold voltage device, they are known as high VT devices, and there are some transistors with low threshold voltages known as low VT devices. So, if your circuit demands speed, okay, so you design using low VT transistors, and wherever you need low leakage devices, you require high VT devices there. So, there that is why if you so the high VT devices, the threshold, the leakage currents could be around 10 picoamps to 100 picoamps, but the low VT transistors, their leakage currents could be around 10 nanoamps or 100 nanoamps. So, it all depends upon your application. The question is what is the function of passivation nitrate? Okay, passivation, I hope I'm not sure which nitrate are you talking about. Is it if you build the chip, or there is something known as a final passivation is there. So that passivation, so once you construct the chip, you don't want any other external impurities or nothing coming into this one. Okay, so the nitrate is a good material, and there are other materials like polyamide and all. So, this nitrate, the diffusion coefficients of most of the species are very small in nitrate. Okay, so that is why people typically use nitrate there. So that is one of the simple examples. Also, you cannot oxidize. One of the reasons why you can create silicon dioxide by oxidizing silicon. Okay, but you cannot nitrate the silicon and create silicon nitrate. That is because the diffusion coefficient of inside the nitrate, whatever the species is very small. Okay, so but that property you can use it as for passivation purpose. That is, you don't want any alkali ions, or we saw that in the CV characteristics you can have alkali ion contamination, because so you put a passivation materials, you block all these impurities, so that it from reaching from the device layer. Next question is, how can we optimize power dissipation if you decrease threshold voltages at a different gate lengths? Optimize power dissipation. So, if you reduce threshold voltage, okay, so your off current is going to increase, but your power dissipation you mostly do, it depends on your circuit, right. So, circuit, there are various ways in which you can do power. There are a lot of power management strategies in circuit design. So, you don't control your power dissipation at the device level. Okay, device level, it gives you a choice of different transistors with different power leakage levels and different speeds. So, it is up to the circuit designers to use, like employ, okay, how should I use this different flavor of transistors and then come up with my circuit. Okay. So, the next question is why metal 2 is not used for interconnection? No, metal 2 is also used for interconnection, but in very early days people the circuit complexity was not very big. Okay, so maybe people could do with a polysilicon. Okay, using doped polysilicon also you can make interconnects, and using metal one, single metal also people could make interconnects. But circuit complexity has increased. That means if the number of transistors has increased, then you need to use additional metal levels. Okay, so that is why it is called a multi-level metallization. So, you need more levels of metal. In some of the advanced chips now, okay, it may have some 15 levels of metals. So, you require, for example, simple SRAM, okay, you cannot build an SRAM with only one metal, okay, you require 2 metal levels at least. In FinFET, either leakage or dynamic power is more. Okay, I will come to FinFET in a minute, but the FinFET also has leakage current, but the leakage current with in comparison to the planar device, it is much lower. That is because it has more gate and it has more gate control. But the dynamic power, it depends upon your VDD, it depends upon your switching frequency, it depends on your capacitance and all. In the case of anti-punch through, if we dope heavily, then how can we manage gate length for our security? No, the anti-punch through implant, keep in mind, it's a deep implant. Okay, this this punch through implant, your goal is to dope the region heavily somewhere in the deep. Okay, so your peak of that concentration will be somewhere in the mid. So you don't want the drain coming and talking to the source subsurface, but you don't want very high concentration at the surface. Okay, you don't want for example, whether the simple question is, suppose I dope my entire substrate heavily. Okay, all I am my main worry was anti-punch through implant, and I doped the entire substrate heavily. What's the issue? Okay, there are a couple of issues. One is your VT is determined by your doping. Okay, suppose if you want to reduce the VT, you cannot do that because you are doped the substrate uniformly. Other thing is that your drive current, okay, it depends on some quantity known as mobility. Okay, this mobility, if your doping concentration is high, you can have higher large number of scattering events with the impurity events. So the mobility reduces. So you don't want very high doping concentration at the surface, but so it's a real engineering problem, right? There's a lot of trade-offs are there. So you have to carefully optimize your doping profile, keeping all these things in mind. Okay, in inverter, in place of polysilicon, other materials can be used or not? I'm not sure I understood the question. Okay, are you talking about whether you can use any other material for gate instead of inverter as polysilicon? In that case, yes, the modern day devices, they may use metal gates. Okay, so you can use metal. So in all similarly, in very early days, we saw that people were using aluminum of a gate. So from aluminum gate technology, people switched from silicon gate technology in early 70s. So then we are again going back to metal gates now.